development study of yield, 4 factors were studied, each at 2 levels: time, concentration, pressure, and temperature. A single replicate of a 2 to the 4 design was run, and the resulting data are shown in the table P6.7. Construct a normal probability plot of the effect estimates which factors appear to have large effects. Conduct an analysis of variance using the normal probability plot in part A for guidance in forming an error term. What are your conclusions? Write down a regression model relating yield to the important process variables. Analyze the results from this experiment. Does your analysis indicate any potential problems? Can this design be collapsed into a 2 to the 2 design with 2 replicates? If so, sketch the design with the average and range of yield shown at each point in the cube. Interpret the results. Construct a normal probability plot of the effects. First, we need to get those effects, and to obtain them, we are going to realize the Yates algorithm, starting from the data of the yield. The first thing you need to do, you are going to add the first and the second data. Then you're going to add the third and the fourth, and so on until you finish with the last two. After this, you're going to subtract the second with the first one, the fourth with the third one, and so on until you reach the last value. This is for the first Yates algorithm. You need to follow these steps until you reach the fourth algorithm. The next algorithm, that will be 2. You are going to add the first one and the second of the first algorithm, and so on. And also you are going to subtract the second and the first one of the first column we got until you reach to the last value. At the last algorithm, the next step is to get the effect column. To obtain the effect, we're going to follow this formula. The contrast is the last column we got from the Yates algorithm. The n is equal to 1 because we are not using replicates, and the k is the number of the sign, which would be 4. We select the first constant, which is 36, over the n, which is 1, times, you open a parenthesis, 2 to the 4, that multiplies 0.5. And this is the first effect. And so on. You need to do it with every value of the last Yates algorithm, which is the construct column. Once we get the effects, we are going to paste them in a new table. But you need to paste them just the values. And also you're going to copy the sources and paste them in here. So the next thing you're going to do, you're going to select the sources and the effects, and you are going to filter them from the minimum value to the maximum value. Okay, and that's it. To make a correction, this is how it's supposed to be. What you have to do is to get the probability of every place. The formula is very simple. It is the first place minus 0.5 over the total number of places you have, which in this case is 15. Okay, when you get this table, you are going to plot these values, and this is the plot that we get, which is the Daniel test. And according to the following data, we assume that the sources AC, C, D, AD, and A are separated from the rest, from these ones. So this is going to be the AC, this is going to be the C, this one is the D, and this one is the A. So these sources with their own factors appear to have a larger effect. For the analysis of variance, also called the ANOVA, we're going to pick the sources that appear to have larger effects. which in this case was AC, CD, AD, and A. From each source select, we are going to fill the next table. We're going to make a sum of squares, difference of freedom, the MS error, the F, and the F table. To do the sum of the squares, we are going to follow this formula, which is the contrast to the square over n times 2 to the k. So the thing is, we are going to select the contrast of the AC, which is this one. And we elevate it to the second power. Then what we get, we are going to divide it over n, which is 1, times 2 to the k. The k is the number 4 because we are doing a design with the fourth value. We are going to do the same for every single contrast of each source that we are making. So for example, the C, we're going to pick the 16 and we elevate it to the second power and we divide it over 1 times 2 to the fourth. And so on with the D, with the AD and the A. Get the total sum of the squares, we are going to make a sum of the squares of the yield, which is this column. And we're going to subtract to the Hulk. The Hulk is going to be this one in green because it's the greatest value of the J's algorithm. This one is going to be elevated to the second power, and what we get, we are going to divide it into 2 to the fourth, and this is what we get. And for the error, we are going to subtract the sum of all the sources we got to the total. The degrees of freedom for every source is always going to be 1, and for the total is going to be 15 because of the 16 values we have. We subtract the 1 in order to get the degree of freedom. To get the MS, we are going to divide the sum of the squares of the source over its and this one is going to be the MS error, which is very important because to get the F value of each source, we are going to divide the MS of the source over the MS error. And these ones are the values that we got. If you check it on the F table, you're going to get the value of 4.965. Because the F value that we obtain are greater than the F of the table, our conclusion is that we reject all the null hypotheses because the values of F are smaller than the F we obtain. As I said, this means that in effect the selected sources have larger effects. So the sources that we analyzed before actually have larger effects on the design. To make the regression equation, we are going to follow the next formula. The whole term is the name given to the first value of the last 8 columns. In other words, the green value. We are going to use the effects of the sources that we previously used. That would be AC, CD, AD, and A. But the effects will be divided by 2. Once we make all this, we can say that we create the regression equation. So you just follow this equation. If you obtain the result, that is the regression equation. Next, we're going to obtain the residuals. To obtain them, we are going to use the table of signs and the regression equation. This is the table of signs. We're going to copy the values of the source A, for example, and we are going to paste them below the corresponding source in the regression equation. And this is how we're going to arrange these values. Next, we are going to substitute the formula, and the value we get is going to be the expected value. Observed values are the values that we obtained previously, which in this case, those values are called the observed. And to obtain the residuals, we are going to obtain the difference of the observed minus the expected value, and so on. These are the residuals we get. To check if the design can be collapsed into a 2-to-3 design with 2 replicates, we need to obtain the F mark of each source. To get them, we are going to use the table of signs and the residuals. We are going to get the positive variance and the negative variance from each source. To get the positive variance of a source, we're going to take the values +1 from the residuals, and we ignore the values that are -1. For the negative variance, it's the same, but vice versa. Once we get the positive variance and negative variance for each source, we apply a natural logarithm of the positive variance over the negative variance. What we get is our F mark. To make it simple, I use a formula called in English if. And for example, if this value is negative for the positive variance, I'm going to name it false. But if it's positive, I'm gonna make it take the value of the residual that is next to the source A, which is 0.875. And so on. I'm gonna make all this table. And it is simple, because then when I make it variance positive, I just call the function var point s of this column, and I'm going to get the variance for positive for the source A, and for the negative is exactly the same, but vice versa of what I do here. If it's negative, I'm going to take the value. If it's positive, I'm gonna make it false. And then the F asterisk is just a natural logarithm of the positive variance and the negative variance, positive over negative. Values of the F mark that I get from each source, I'm going to copy and transpose them into a new table. These values, I'm going to arrange them from most negative to most positive, from minor to the greatest. And in a normality test, the dispersion tells me that only A and ACD affects, because B is not in the dispersion in the normality test nor in the location. I can tell B does not affect the dispersion nor the location, so it can be collapsed into a 2-to-3 design with 2 replicates. Because it can be collapsed, I'm gonna design a cube. First, we should state our reference, and once we do that, we can start pointing the values of the GL. My origin always is 1, and because this one goes to the right, this one is going to be the A, this one, the C goes up, my point is going to be the C, and the D goes like in this direction, this one is going to be D. And for example, if this intersects over here, the point 3 is going to be AD. Point 4 is going to be ACD because it intersects A, C, and D. And so on with all the points. And because B does not affect, you are going to add a little bit to the points named before. So for example, the point 4, I have ADC, I'm going to add the B. ADCB is going to be my other point. All the sources in the point, I'm going to copy the values of each source. And then I'm going to get the average for each one and the range for each one. And this is how I get my cube in a collapse design.